Our project is called Energy on the Move, analyzing a vertical dual spring system for energy efficiency. In this phase, we built a physical prototype of a vertical dual spring system to observe its oscillatory behavior and compare it with the mathematical model we previously developed. The purpose is to simulate how energy is stored, transferred, and dissipated through a double spring system, similar to what happens in elevators, shock absorbers, or vibration dampers.
Okay, so we did the prototype using simple household materials. First of all, a cardboard tube from a paper towel roll to guide the vertical motion. Two small springs, one at the top and one at the bottom, connected to a small mast made from bottle caps and cardboard. This was the cabin. A cardboard base on the bottom and a cap on the top to support and limit the movement. A tape and glue to hold the structure together. And the mass moves vertically inside the tube between two springs, which compress and extend alternately as the system oscillates. This setup represents a damped double spring system because friction and internal resistance gradually reduce the amplitude of motion.
What's the functionality of our prototype? When the cabin, that is the mass, is displaced and released, both springs interact. The upper spring compresses while the lower one stretches, and vice versa. The energy alternates between potential in the springs and kinetic in the moving mass. Over time, damping effects like air friction and internal material losses cause the oscillations to decrease. This represents a smooth motion system, similar to an elevator cabin or suspension system where the goal is to avoid hitting the extremes and allow a soft and controlled displacement.
The reasoning behind choosing this model is because it clearly demonstrates the energy exchange in damping behavior in a real-world system. It connects with applications such as elevator safety systems, vehicle suspension, and vibration isolation devices used in civil and mechanic engineering. It also relates to SDG 9, Innovation and Infrastructure, and SDG 11, Sustainable Cities, since these technologies improve efficiency, comfort, and safety in daily life.
As a conclusion, this prototype allows us to visualize how theoretical equations translate into real motion. It helps us to understand how dual spring systems behave dynamically, how energy efficiency can be improved by reducing vibration losses, and how damping ensures safe operation in mechanical systems. Our next step will be to record the motion, measure its frequency and damping rate, and compare it to our numerical simulation.